Hi everyone! Finally, I had the time and energy to share with you an overview about my master thesis investigations about the two low power wide area network technologies, LoRaWAN and MIOTY. If you have any constructive feedbacks or questions, please write it down in the comment section. I'm Ons and this is IoT information out there with Ons. Actually, before tackling any subject of this research, we need to know why this research actually is making sense. Why are we comparing two technologies, LoRaWAN and MIOTY? Actually, LoRaWAN and MIOTY have much similarities. First of all, they are both a part of the unlicensed low power wide area network technologies. Second of all, they are both having the same duty cycle restrictions. And third of all, they have typically the same network architecture, and this is really very interesting. They have both the star of stars architecture, going from the endpoint to the base station, and then to network server, application server, and then going through to the IoT platform from the user interface. But the main differentiating factor here between LoRa and MIOTY is the technology or the modulation used. LoRa uses the chirp spread spectrum modulation, and MIOTY uses the telegram splitting ultra narrowband technology. Actually, within this telegram splitting ultra narrowband technology, MIOTY said, I perform better in the industrial environment. I'm better when it comes to the industrial Internet of Things or the massive IoT. Thus, my research is about LoRaWAN and MIOTY in a real industrial environment. So to test this real performance in a real life, in a real industrial environment. Now I will share with you my investigations and the results that I have found. Actually, I published a research paper in ResearchGate. This paper is like an overview or an abstract about my master thesis research. And now I will go through this paper. I will explain all the parts in the paper, and I'm really looking forward later for your constructive feedbacks, your remarks, and further information. The main objective of the investigations actually is to test both technologies, both LP1s, LoRaWAN and MIOTY in a real industrial environment, while ensuring a fair benchmarking as possible and taking into consideration two main metrics, packet reception rate and energy consumption. Now let's focus on the first metric. What is packet reception rate? Packet reception rate is the percentage of received packets after being sent from the transceiver to the receiver. In other words, and this is how I like to call it, they are the number of survived packets after passing through the base station, the network server, application server coming to the IoT platform. In this research, the packet reception rate is the percentage of packets being received by the user interface after passing through the gateway, network server and application server. Because in other words, in other research, packet reception rate could be only the number of packets on the gateway, so received by the gateway or by the network server. But in our case, we are testing on the user interface point, so they are the number of packets being received in the IoT platform part, and we will explain this later actually. Why this metric is actually important? Because it gives an idea about the technology performance, resilience to interference, and range. And this is how we can compare both technology and say, okay, the technology having better percentage of the packet reception rate is meant to perform better. How we are doing this? It's just a simple calculation. We are sending packets. We know the number of packets being sent by the endpoint. And then we, within a script that we will talk about later, we are calculating the number of received packets, and then we will know how much packets are being lost and how much packets are received, and then we will calculate the packet reception rate. As I have mentioned before, LoRaWAN and MIOTY have nearly the same network architecture, going from the end node to the user interface. Here I have a LoRa end node and a MIOTY endpoint. Those are two different terms for basically an IoT device to say this is a LoRa device or a MIOTY device. Both will send data over the LoRa technology or the MIOTY technology to a LoRa gateway or a MIOTY base station. So this gateway or base station have the role to bridge the data to the network server. The gateway will receive the data from the end node, make the data integrity check. It will also check the receiver signal sensitivity strength indicator. And then if everything is okay with the signal, the gateway will add some extra data like time, signal to noise ratio, RSSI, and then forward the packets to the network server and application server for authentication and decryption. On the other way, if the RSSI is so much bad, or if the signal is corrupted, or there is missed frame, the gateway will just throw the packet and will not forward it to the network server and application server. Coming to this part means application server. I can say that we are no more talking about LoRaWAN network architecture or MIOTY network architecture. The data here are totally decrypted and ready to use. And what we choose to make is to have the data in a MQTT broker. If I want to be more precise, a Mosquitto broker. So we publish the data to Mosquitto broker, and then within a Python script, we subscribe to the data we need, and then we make our tests. Like we analyze the RSSI, the received packets, and then we make our calculations. Until this point, actually, everything seems to be ordinary. There is nothing really so much special. But what is really special in this research, and what really makes me feel excited to make it, is that we are using the same hardware for both technologies. Like the same hardware, literally use it for LoRa and MIOTY for the tests. So this is our hardware used for the end devices. The same hardware for LoRa end node and the same for MIOTY endpoint. We have here a printed antenna. We have here an STM32L microcontroller to control this board. And we have here the important part, the RF module. The RF module from Murata is called APC module. It is also having an STM32L microcontroller and an SX1276. It is a Semtech transceiver. We are used to have the Semtech transceiver SX1276 for LoRa, but because it supports also the FSK modulation, it could be also working for MIOTY, and this is how we manage it to have the same board for LoRa and also MIOTY. Actually, we did not only use the same hardware for the endpoint, but also we have used the same gateway or the base station. It contains two modules, MIOTY and LoRa, and to guarantee that they are also using the same antenna, we fed the two transceiver with the same single rod antenna using a passive splitter. Yeah, I know that the passive splitter is adding attenuation of 3 dB, but if this attenuation is affecting both technologies, so our investigation or our research is still making sense because it's affecting both. And on the last part, I want to mention here that we use the Raspberry Pi 4 in which our broker is 24/7 running. So here we talked about the network architecture used, the hardware used, and the software for our use cases, right? So now let's go to the implementation and tests. We have here our end nodes or endpoints. We have here the board we have talked about, and then we integrate some sensors. Of course, we need some data. We have here two temperature sensors, one for LoRaWAN and one for MIOTY, and two time of flight sensors, one for LoRaWAN and one for MIOTY. So in total, we have 4 devices. So in this test, LoRaWAN and MIOTY are in uplink mode, means class A for LoRaWAN, class Z for MIOTY. There is no retransmission. They use both the same power of transmission, 14 dBm, And for LoRaWAN, you used LoRaWAN spreading factor 12 because it's considered as the best performance spreading factor. It also risks more energy consumption, but we are now just talking about the packet reception rate. So we were not calculating the energy consumption here. The end devices send data every 10 minutes with a packet payload of 10 bytes. And this is our hybrid base station. The base station is having a very great position on top of the roof. We have here our rod antenna. We have here our hybrid base station covered and protected from the weather. Our end nodes or endpoints are placed every time in different location. We have 5 scenarios, means 5 locations. The first scenario is, as you can see here, with this red dot, this is our antenna. It's directly near the antenna. We wanted to test the direct line of sight scenario to make sure that we are receiving 100% of data, so nothing is wrong with the devices or the base station. The scenario number 2 here, I consider it as the very hard environment, or the hardest scenario, because we placed the devices in the basement, which is about 85 meters away from the base station in the horizontal axis and about 24 meters in the vertical axis. And actually, why I consider this as a very hard position, because between position 2 and the base station there are much buildings and they are full of dense Wi-Fi and structure, so there is much opportunities for interference and signal corruption. Scenario 3 was outdoor scenario, and it was an office space actually. Scenario 4 was the only scenario outdoors. It was the sensors were placed in the main entrance, which is about 107 meters away from the base station in the horizontal axis and 18 meters in the vertical axis. And scenario 5 here, it was the production site. It was also a dense place with much interference and obstacles. Now let's check the results that we have found. Our test scenarios are summarized in this table. We have here scenario column 1, 2, 3, 4, and 5. We have here the distance from the device to the base station, number of sent packets, packet reception rate of LoRaWAN in spreading factor 12, packet reception rate of MIOTY. Scenario 1 is the direct line of sight scenario, so we expect that we are receiving 100% of the packets in the LoRaWAN and MIOTY case. Scenario 2 is considered as the hardest scenario. We sent 696 packets and we received none packets from LoRaWAN side and 14.3% from the MIOTY side. This use case, the packets actually from LoRaWAN were seen in the base station. There is packet being received. So the endpoints or the end devices, the end nodes from LoRaWAN sent packets to the base station. And then the base station, I assume the packets were thrown and ignored because they does not make sense. They are corrupted or they have a bad RSSI. So they couldn't be seen in the user interface part. For scenario 3, we have the biggest number of sent packets, 3,508, and the packet reception rate of MIOTY was 58.9, and for MIOTY was 75.3. For scenario 4, we sent 601 packets and we received 69.7% for LoRaWAN and 72 for MIOTY. For scenario 5, we sent 265 packets. We received 61.9 packets. And for LoRaWAN, spreading factor 12, and for MIOTY was 86.8%. So, to summarize, according to these results and these special scenarios and our use case, we can just conclude that MIOTY is performing better or is more robust in obstructed environment than LoRaWAN. Now let's talk about the second metric, energy consumption. What is actually energy consumption? Why it's important for this research? Energy consumption is the amount of energy consumed by the IoT device during the transmission, and it is calculated in milliwatt hour and gives the idea about the battery life. Why energy consumption is considered as a metric for this research? Because it's a crucial factor, especially for low power technologies. It helps estimate the battery life for both technologies. And we know that LoRaWAN and MIOTY are based on low power. So calculating the energy consumption is a good factor of comparison in our case. How we are doing this comparison? Actually, by using the OT-ARC tool, we were able to calculate the energy consumed during active mode and sleep mode, thus calculate the battery life estimation in months. And this is battery life estimation also is calculated automatically by the OT-ARC tool. This is actually how the tests look like. We have simply the OT-ARC tool and we are connecting it to the end node for LoRa and the endpoint for MIOTY, and thus we are having our battery life estimations. The OT-ARC tool enables us also to see the signal. For example, here this is a screenshot from the OT-ARC for MIOTY signal. We have here start sending. We can see here the small frame being sent over the time, and then the sleep mode starts. The same for LoRa. LoRa starts sending, and here we have the LoRa signal, and then after sending the message, the two downlink window will be opened. This is in class A, and then it will enter in the sleep mode. The OT-ARC asks for some specific information like the battery used and how much time the device is sending, and then it will give automatically the battery life estimation. The results are summarized in this table. We have here energy consumed in microwatt hour for LoRa adaptive data rate, spreading factor 12, spreading factor 10, 9, and 7. The energy consumed in the energy consumption in active mode, also in sleep mode, and then we have the battery life estimation in months. The adaptive data rate here and spreading factor is showing nearly the same results. I assume because the adaptive data rate we're also using the spreading factor 12 regarding the distance between the end nodes and the base station. We have here the highest battery life estimation in months was in spreading factor 7, 9 months and 9 days. So, and this was expected actually because the spreading factor 7 in LoRa is the one guaranteeing more or better battery life. For MIOTY, we have 10 months and 2 days. So MIOTY is still showing better results in terms of battery life estimation within the same hardware and the same conditions. This research entitled LoRaWAN and MIOTY, a study on packet reception and energy consumption in the industrial Internet of Things, aims at comparing both technologies, LoRaWAN and MIOTY, in a real industrial environment, taking into consideration the packet reception rate and energy consumption as metrics. This research has shown that MIOTY is performing better than LoRaWAN in these defined scenarios, even though LoRaWAN was in spreading factor 12. Nevertheless, this research has its own limitation and more research and expertise needs to be done to make more proof of concepts. For example, we need to know the impact of retransmission feature of the results, the downlink feature of LoRaWAN and MIOTY. This is a very important feature to test. And of course, using much more devices will also give better result or better comparison results.
Thank you so much for your priceless time. I really hope that this research or my investigation was helpful for you, and please, it would be highly appreciated if you subscribe, like or share this video. That would really help me to do much more efforts and share more videos on my YouTube channel. Thank you.